Hello. Today I'm going to be talking to you about Delta-CRDTs. For those that are not familiar with CRDTs, CRDTs stand for conflict-free replicated data types, and they are specially designed data structures to achieve strong eventual consistency when replicated. So they can be very important to decentralized systems as each one of the peers holds a different replica of the same data, and they can perform changes locally, and those changes can be later replicated to other participating nodes, and that replication can be done asynchronously, and CRDTs um, guarantee the convergence, so that all the nodes uh, eventually converge to the same state, and so they all see the same data if the operations stop and messages are fully exchanged, etc. So CRDTs was first coined in, I think, this paper, 2011, um, and there are two main CRDT types. So the first one is operation-based CRDTs, and each operation, uh, each mutation that you do locally creates an operation that is appended to an operation log. And that operation log is what is replicated between different replicants over the network. And so as you get a replicate gets a new operation, it applies that operation onto itself. And uh, and so you have to keep so the messages contain the operations, and you have to keep the operations around in case a node requires them. In contrast, state-based CRDTs don't have the concept of operations. They have the local mutations return a new version of the state, and that new version of the state or can be what is transmitted to other nodes, or you can just transmit internal state to other nodes later in time. However, it fits your needs, and so um, state-based CRDTs have different characteristics than operation-based CRDTs because they can be messages can be lost and delivered out of order if you want to. If you require to, it doesn't compromise the convergence. So if a message containing the entire set is not yet delivered, it will be delivered later. If it is delivered later, then the effect will be applied later. And since they contain the entire state, they don't have to be in any specific order. Um, the order can be swapped, and they always guarantee convergence. Um, and state-based CRDTs are not very practical because the state can be quite big, and to transmit that over the network to all the peers may be uh, maybe not very feasible, not very performant, depending on the size of your internal states. And and so a middle ground was created called Delta State Replicated Data Types, Delta-CRDTs. And the main difference is that mutators don't return the entire state. Mutators return a delta, which can be seen as a fraction of the state that changed. And then these are different from operations because deltas can be forgotten, and in worst case scenario, you just send the entire state. And deltas uh, can be combined into one bigger delta. So, for instance, if a node is behind on your latest four deltas, you can combine those four deltas into one delta that is smaller than the four deltas in separate, but combined it creates a smaller message, and then you can send that delta only using the network in a more optimal transmission. of the state. And there is a JavaScript implementation of Delta-CRDTs. You can install it using Delta-CRDTs package on npm. I'm going to try and make a little demo of that. Let me remove, so npm install Delta-CRDTs. Cool, so we have the package created, installed, sorry. So let's require it. So I'm going to store it here in this variable, Delta-CRDTs. Now we have that imported. We can now create a type or instantiate a given type. This package already comes with a bunch of CRDT types. Different types for counters, flags, sets, arrays, one type of array, and registers. And you can also extend that by creating your own CRDT. The difference between the different types is mainly can be the way that the CRDT handles concurrency. For instance, in this flag, you can have two mutators, enable and disable. And if you use an enable wins flag, if different replicas concurrently do an enable and the other does a disable concurrently, enable wins means that the enable will win, and disable wins means that disable will win on this concurrency scenario. So depending on your merge, your join semantics, the join semantics that you want, you may want to choose different CRDT types and or even create your own by extending it. So let's see that in action. So we're going to use an array which has an internal state which is complex. It's called RGA. Internal state that is complex, but it exports a JavaScript array view value of the state. So let's create that. So RGA equals CRDT RGA. So that we have the RGA type, that's a function that we can use to create different replicas. So right now, this Delta-CRDTs doesn't really care about network. It's just a local library, but we can simulate network by assigning messages to variables and then transmitting that over, applying that to different replicas. So let's create a replica one with RGA constructor requires all the type constructors require the peer identifier. So let's call peer1. Okay, it's a string R1. We have R1. Now let's create a replica 2 called peer2. Okay, we have two replicas. So R1 different values with the same value, empty array. So let's do some operations. So R1 has a bunch of mutators. So can push, remove, that, remove that, and so the typical array-like operations. So let's just do a simple push. R1.value is this one. So let's do another push of B. Okay, so R1.value. So R2.value doesn't have those elements yet. So a way to transmit that is to get entire states. So let's store that into a state variable called state of replica 1 equals R1.state. Let's say that we encode this and send it over the network, and it gets to replica 2. Now replica 2 has state 1. It doesn't know what's inside that. It's just going to apply that into its own state. So R2.apply state 1. And now R2 value should contain, and it does contain, the new elements of the array in the order that were inserted on R1. Okay, so now let's try and do some concurrent operations. So R1 dot push, let's see C, okay, and R2 dot push D. Okay, so now we have different values for both replicas ABC and ABD. And so let's exchange messages with the entire state and apply them locally. So instead of storing that state, I can store that here. So our is state one is r1.state, and now state two is r2.state. So let's apply r1.apply. That's transmitted over the network, and then bloop, it comes out the other way, and I'm going to apply that. So state two here, and then the vice versa, r2.apply state one, got the message from replica one, and apply. So let's see what is the value. R2.value is ABDC, and R1.value is ABDC. So they both converge. And D is before C because it was an operation that was created later than C. So as a later timestamp than C. But the thing is that both of them come after B because they were pushed after B, and both replicas have the same exact view value, which is the important thing. One of the important things. All right, so right now we're just using states, so let's try and use deltas. So let's create an array to store deltas. Deltas for replica 1 is here, and then deltas for replica 2 will be stored here. So as I said, mutators return the delta instead of the entire states. So let's push that into the array as we mutate locally. So deltas 1 dot push, r1 dot push. So we're mutating here and then pushing that delta into deltas 1 array. Let's bcde. Let's push the value e, and then f. So right now R1 has a value that ends in EF. R2 is still lagging behind. So, but let's create some operations on replica 2. Deltas 2 dot push replica 2 dot push G, for instance, and H. So R2 dot value ends in GH, where R1.value ends in EF. So let's get them in sync by applying each other's deltas. So we have two deltas, deltas 1, we have two deltas on deltas 2. Let's exchange them, transmit them over the network, bloop, and then now each one of the replicas has each other's deltas. So let's say R1.apply deltas. Have to apply each one of them. So deltas 2 dot for each delta, and then R1 dot apply delta. Okay, so now R1 dot value should have ends in EF. R2 dot value doesn't have yet EF. Sorry, R1 has GH, which were the operations, the insertions that replica 2 did. Now replica 2 is missing replica 1's deltas, so let's apply that. Instead of doing this, I'm going to do deltas 1 dot for each, and then directly put the method here. So R replica 2 dot apply here. So R2 dot value should be the same as now as R1 dot value, so they both converge. Cool. So now we're sending the deltas over the network one at a time. Let's see the power of joining deltas now, for instance. So let's create more mutations on replica 1 and more push mutations, for instance. I. Let's push I, and then first I'm going to reset deltas 1, reset that, and then I'm going to push. Where was I? Deltas 1 dot push. Let's ghi r1 dot push. So I'm going to do a push on replica 1, inserting I at the end, and I j k. So now we have r1 dot value as I j k at the end. R2 doesn't have, and we have deltas 1 dot length, 3 deltas. So let's reduce that delta. Now we know that R2 is behind on 3 deltas. So let's compress those three deltas into one delta. I'm going to call it big delta, and I'm going to deltas one call deltas one dot reduce, and the reduce function is the join function of the type, which is rga.join. Is exposed here. Every type exposes a join operation which is specific to that type, and also the initial value state will be rga.initial. Initial, which returns the initial state of that type, which is represented in an empty array. So now we have big delta, which is more compact than those three separate deltas. But let's send them over the network from replica 1 to replica 2, and then apply that to replica 2. So R2.apply big delta. Okay, so now R2.value has I, J, and K, and it's the same as our R1.value. Cool. So that concludes my episode for today. Hope you enjoyed and hopefully learning about Delta-CRDTs and Delta-CRDTs in JavaScript. And hope to see you on the next episode. Bye bye.